Simultaneous systems of differential equations from Hoy, chapter 24. Now, in economic models, it is common for two or more variables to be determined simultaneously. Dynamic economic models may require the solution of a system of differential or difference equations. And the simplest case is a system of two linear differential equations. Such a system can be solved using the substitution method, or more generally, using the direct method. Let's look at the substitution method first. We will start by looking at the substitution method. The method is applicable to systems consisting of exactly two linear differential equations. So y1 dot is equal to a11 y1, a12 plus a12 y2 plus b1. y2 dot is equal to a21 y1 plus a22 y2 plus b2. The system contains only linear differential equations, and the system is also autonomous because look at the powers of y1, y2, and y1 dot and y2 dot. None of the powers exceed 1. They're all equal to 1. So this is a linear system. The system is also autonomous because B1 and B2 are constants. And the solutions for y1 dot and y2 dot depend on both y1 and y2. So they must be solved simultaneously. Now, as always, the complete solution to both equations is the sum of the homogeneous and particular solutions. So we have y1 is equal to y1h plus y1p, and y2 is equal to y2h plus y2p. Let's look at the general solution to the homogeneous form. The homogeneous forms of the two linear autonomous differential equations are y1 dot and is equal to a11 y1 plus a12 y2, and y2 dot is equal to a21 y1 plus a22 y2, right? We've gotten rid of the constants, so they're now homogeneous. Differentiate equation 1 and obtain y1 double dot is equal to a11 y1 dot plus a12 y2 dot. Plug this expression, right? Plug in 2. So equation 2 is y2 dot. We have a y2 dot over here. Plug equation 2 into this expression. So when you plug in 2 for y2 dot, you will get y1 double dot, right, is equal to a11 y1 dot plus a12 times a21 y1 plus a22 y2, right, from here. Also from equation 1, we obtain an expression for y2, which is equal to y1 dot minus a11 y1 by a12, which we can plug into equation 3 and get y1 double dot is equal to a11 y1 dot plus a12 times a21 y1 plus a22 times y2. So we replace y2 with this expression over here. Now, when we simplify it and rearrange it, we get y1 double dot minus a11 plus a22 times y1 dot plus a11 a22 minus a12 a21 times y1 is equal to 0. So equation 4 can be recognized as a linear homogeneous second order differential equation with constant coefficients of the form y double dot plus a1 y dot plus a2y is equal to 0. We know the solution to such an equation depends on whether its roots are real and distinct, real and equal, or complex. Now the characteristic equation of equation 4, this equation, right? The characteristic equation of this equation is r squared minus a11 plus a22 times r plus a11, a22 minus a12 times a21 is equal to 0, with roots r1 and r2 given by a11 plus a22 by 2 plus minus 1/2 the square root of this thing. Now you can obtain this expression by using the quadratic formula. Once you have obtained the roots r1 and r2, the solution to equation 4 is y1 H, the homogeneous solution, is C1 e to the power R1t plus C2 e to the power R2t. R1, R2 are real and distinct. Y1H is equal to C1 e to the power RT plus C2 times T e to the power RT. R1 and R2 are real and equal. And Y1H is equal to e to the power HT times A1 cos nu T plus A2 sine nu T. R1 and R2 are complex, where H is equal to A11 plus A22 by 2. And nu is equal to half of the square root of this thing, right? 4 times A11, A22 minus A12, A21 minus A11 plus A22 whole squared. Now we have obtained Y1HT. What about Y2HT? Now there will be different solutions for Y2HT depending upon the nature of the roots of the characteristic equation. We will begin with the case of real and distinct roots. The starting point for all cases is to recall that Y2 is equal to Y1 dot minus A11 Y1 by A12. So the starting point is this expression, right, which we obtained from equation 1. Y2 is equal to this thing. So we start with that expression. Now, for the case of real and distinct roots, Y1 is equal to C1 e to the power R1t plus C2 e to the power R2t, which implies Y1 dot is equal to R1 C1 e to the power R1t plus R2 C2 e to the power R2t. Plug these expressions for Y1 and Y1 dot into the above equation for Y2. So we have this equation Y2. You replace Y1 dot with this expression. You replace Y1 with this expression. And you get this expression. Simplify it. And once you have simplified it, it gives you Y2H of t, which is equal to R1 minus A11 by A12 C1 e to the power R1t plus R2 minus A11 by A12 times C2 e to the power R2t. So the fundamental solution for Y2H is pretty much the same as for Y1H, right? It still has C1 and C2, but they're multiplied by new constants. But the basic form of the solution is the same. Now you can repeat the procedure for the case of real and equal roots and complex roots. So what you need to do is to differentiate the appropriate homogeneous solutions, Y1, to obtain Y1 dot, then plug both into this expression, right, into the above expression for Y2 and simplify. You will then get the required Y2H. The results are summarized in the next slide. So this is the summary of the solutions. Okay, so you have this solution for real and distinct roots. You have this solution for real and equal roots, right? And R1 and R2, when they are real, are equal to these things, right? This expression. When the roots are complex, you have this solution. And again, H is equal to A11 plus A22 by 2. And nu is equal to 1 by 2 times the square root 4 into A11 A22 minus A12 A21 minus A11 plus A22 squared. Now, what about the particular solutions? We make use of the steady state solutions Y1 dot equal to 0 and Y2 dot equal to 0. Now recall that our original system of differential equations was Y1 dot is equal to A11 Y1 plus A12 Y2 plus B1, and Y2 dot is equal to A21 Y1 plus A22 Y2 plus B2. When we plug in Y1 dot is equal to 0, Y2 dot is equal to 0, we obtain 0 is equal to this thing, and 0 is equal to this thing. You need to solve these two simultaneously for Y1 and Y2. Please do it. And when you do it, you will get Y1 bar is equal to this expression, and Y2 bar is equal to this expression. And these are the particular solutions. And you need to simply add Y1 bar and Y2 bar to the homogeneous solutions in order to get the complete solutions. And these are shown in the following slide. So we have the complete solution to the system of two linear first order differential equations for real and distinct groups, for real and equal groups. So it's the same slide as before, but we've added y2 bar and y1 bar, right? y1 bar and y2 bar have been added. Everything else is the same. We again add y1 bar and y2 bar, and y1 bar is equal to this expression and y2 bar is equal to this expression. Now let's look at an example. Let us solve y1 dot is equal to y1 minus 3y2 plus 1, and y2 dot is equal to y1 by 4 plus 3y2 plus 2. To find the homogeneous solutions, we set the additive constants as 0. So we make this 0, 1, 0, and 2, you get rid of them, replace them with 0. And we proceed as follows. So y1 dot will be equal to y1 minus 3y2 in homogeneous form. And when we differentiate it again, we get y1 double dot is equal to y1 dot minus 3y2 dot, which implies that y1 double dot is equal to y1 dot minus 3 times y1 by 4 plus 3y2. Again, we are working with the homogeneous forms. And from equation 1, right, we have y2 is equal to 1/3 y1 minus y1 dot. Again, we are working with the homogeneous form. So y2 is equal to y1 minus y1 dot divided by 3, right? Homogeneous form. So again, substitute again. So y1 double dot is equal to y1 dot minus 3 times this thing, right? So we replace y2 with this expression and simplify. And upon simplification, we get y1 double dot minus 4y1 dot plus 15 by 4, which is characteristic equation r squared minus 4r by 15 by 4 equal to 0, with roots r1 is equal to 3 by 2 and r2 is equal to 5 by 2. Find them yourself. Thus, y1 is equal to c1 e to the power 3t by 2 plus c2 e to the power 5t by 2, and y2t, this time I'm using a formula. This formula, R1 minus A11 by A12, right? So I'm plugging in R1, A11, and A12, right? So what is R1? R1 is 3 by 2, right? Oops. R1 is 3 by 2. And A11 is 1 from the homogeneous form. A12 is minus 3, again from the homogeneous form. You plug it in here, you get times C1 e to the power 3t by 2, plus R2 is 5 by 2, minus 1 by minus 3, minus A11 by A12 times C2 e to the power 5t by 2. And you simplify, you get this expression, minus 1 by 6, C1 e to the power 3t by 2, minus 1 by 2, C2 e to the power 5t by 2. And you can also find out y2 by differentiating y1 to get y1 dot, and then you plug in y1 and y1 dot into the expression for y2 above, and you will get y2. So you could do it and confirm the result. To find the particular solutions, the easiest way is to simply set y1 dot and y2 dot equal to 0 in the original differential equations, right? And solve the resulting pair of equations simultaneously to obtain y1 bar and y2 bar. So our original differential equations were y1 dot equal to y1 minus 3y2 plus 1. We set y1 dot equal to 0. And y2 dot was equal to y1 by 4 plus 3y2 plus 2. We set y2 dot equal to 0. Solve them simultaneously. Go ahead. And you will get y1 bar is equal to minus 36 by 15 and y2 bar is equal to minus 7 by 15. And so the complete solutions are these, where we have simply added the particular solutions to the homogeneous solutions. Now, if it is given that y1 of 0 is equal to 3 and y2 of 0 is equal to 1, go ahead and find C1 and C2 on your own as an exercise.